Okay, we're going live. Welcome this morning. Thanks for joining us. I know in the session here we have Sonia Mathura here with us on the stream. So thank you for joining. Um, Really targeting a very specific audience with what I'm doing here today, and that is to share the tools that are available for grease sampling, specifically for motor operated valves. So the prompt for this um, it comes from the Nuclear Regulatory Commission, the United States Nuclear Regulatory Commission, that just issued a letter within the last few months regarding an incident where samples were taken at a plant from a limit torque valve. Those samples turned out to not be representative of the condition of the valve, and as a result, there was a subsequent failure. So what I'm describing is available to the public online at the NRC website. You have to search for those parameters to find that. It was brought to my attention by Dave King at the Condition-Based Maintenance Users Group Conference just a couple of weeks ago. So thanks to Dave for bringing that up, and I wanted to use this opportunity to just increase the awareness of what's out there. So how did we get to this point? Well, unfortunately, the tools that were being used for this particular inspection for sampling was tie wrap. So an electrical cable tie, so a plastic tie wrap is what was used in that case, which certainly is an improvement on what I've seen in the past, which was screwdrivers, poking screwdrivers around in the machine and seeing what comes out in the grease. So this is not anything new for me. I can actually turn back the clock to the 1990s when I was in the maintenance department of nuclear power plant Peach Bottom here in Pennsylvania, and there I was brought a whole bunch of samples from MOVs, from actuator gearboxes, and with them I was tasked with the responsibility to sample these several hundred samples that have been taken. Did some analysis, got some results, but they were not helpful at all. And so what we found out was that indeed screwdrivers were used to kind of just put them into that reservoir, see what comes out, and use that for the analysis. At least the tie wrap is an improvement, that you're not going to do any damage while you're in there. You're not going to score any metal surfaces or anything like that. So it's a kind of a softer, less invasive way. But the problem is that the random adherence of grease to anything that you place inside is not going to ensure you get a representative sample. And that includes maybe the follow-up to the tie wrap, which is to just put a plastic tube inside and use whatever comes out. The problem is when you have a reservoir, especially a large reservoir like these gearboxes. So here is one of these MOV actuators. You've got the drive motor here. You can see the stem, the valve stem sticking up right here. Of course, the valve would be down below. If we had one, we just have the actuator at this point. And then this area here, as we move back, is where the gearing is. So you've got this drive motor, you've got a pinion here, it meets up with a second gear. You have a worm gear that moves in this direction, and then that worm gear is going to spin a stem nut. And so this is the application that we're talking about here. So when you get into that space, the problem is you're going to have a lot of grease in there. Not all of it is active in lubricating those surfaces. And not only is it not being used or active, it doesn't have information about what's going on inside the condition. So the condition of the grease that's currently tasked with lubricating those surfaces, the presence of contaminants that could be there, and those contaminants could be dirt, could be moisture, could be the wrong grease, some other substance, and then the consistency of the grease is also very important as well. Has that grease hardened or softened its surface? And that becomes a very important consideration for this particular NRC letter that was sent out, because the samples that were taken with the plastic tie wraps were considered acceptable. What they didn't show that there was hardened grease inside. So we can't just take the grease that preferentially comes out. We have to actively core a sample from inside. And thankfully, like I said, there's been tools around for a long time. When I learned that the screwdriver was not adequate for me back in 1993, I set about to come up with some alternative tools. And so that's really what led to the development of the grease thief, which maybe some of you have heard of before. So let me share with you a grease thief here, and maybe just get a little bit closer for this demo. So the grease thief is a kind of a three-part piece here that has a clear plastic body. So an opening here, a clear plastic body. There is a red piston inside that seals that inner chamber, and then a handle that allows the positioning of that. You notice when I push this forward, the piston moves to the end, and then this particular one has what we call a stinger probe on here. The stinger probe was developed specifically for the MOV so that we could hold this piece, go inside, contact that surface that we want to sample, and then finish up. So the stinger probe allows the body to come forward as the piston stays in place. It almost looks like it's moving backwards, but if you look where the piston is right here, when I hit this surface, notice that the piston stays still and the body moves forward. That's the coring action we need, because now you're going to have something that you can extract that has that last inch or so adjacent to the critical components that we want to be able to sample. And then at that point, we can put this plastic cap on the end and get that to the lab for analysis. Now, what I was just showing you up close, I want to show you the tools that we have that allow this to work in a very controlled manner and getting that targeted grease from those locations. This is the T-handle device. It has a little holding section here. It has a tube section that is moved back and forth. And then there is this rod you can see coming out through the end here. And this rod has a keyhole cutout. Now, two ways to use this device. One is to remove it from this section and just use this tube and the rod that's inside it. So I'll put the adapter down, and I will bring that forward. The keyhole cutout fits right into the handle of the grease thief. It's held in place, and then as I would draw this back, now I can thread this in place. And so I'm spinning this tube section until I get that tight onto that surface, which we have there. Now, remove the cap, and you're going to want to start in this position where the stinger probe is out. Now I'm going to insert that into the machine until I hit that surface, and then continue forward just to sample that last bit. So when you're looking blind, and here's one of the access plugs for the actuator. I'll move that off to the side. When you look down inside, you may see you got direct line of sight to a component you want to sample. Maybe you can't see it because of the grease there, and you don't know how far in. And so you could use this to go in until you contact that surface. Now, that works when you don't know how far to go. But once you understand that, either through looking at drawings or measurements or what have you, and want it to be repeatable, this is where you can move away from the stinger probe requirement and then use the remainder of the T-handle in that case, and then that slides back in place. And this is where we make the adjustment. You have this positioning knob, and once you understand how far you want to go in, you make that adjustment, and then you lock that in place. Once you lock that in place, you're going to get the sample from the same spot every time. And again, you're just going to go into that opening until this stops, till this T part will stop and hold it in place. And then again, I'm coming back here to slide this section to core the sample, and we draw it. So you got two ways to approach. When you're using it in this method, and you don't need this, you wouldn't need the stinger probe anymore because you're fixing the depth inside that you're coring the sample. And this is your improvement there. You could then remove the stinger probe, which we call the type 2 grease thief, the active method. And then there's one that's the type 1. It's the same, has the piston, the body, the handle, but just no stinger probe on the front of it. So these are some of the tools that you have available. It's a major difference in how you approach sampling. And what I want to add to that is that this is, while we over time developed this method, it's not just our thing, it is now an international standard. So ASTM, the American Society for Testing Materials, has a standard D7718, which governs in-service grease sampling. And it's not, I can just say it's not easy to get, it's easy to get a sample, it's just not easy to get the right sample. And that's key, right? In this situation, the NRC cited they got a sample. They were able to extract grease from the inside of this component. It just wasn't the right sample. It didn't tell the story. It wasn't close enough to these components of interest to find this hardened and dried out grease. And as a result of failing to identify that situation, then a significant issue became a problem, including machinery failure. So on critical things like this that are grease lubricated, we want to make sure we get that representative sample. Now that addresses the sample coming from this location in the gearbox. It could be used for an access back here in the motor compartment area. There's sometimes multiple plugs, so you can come in from the side here, come in from the top. And by looking at different areas of engagements of the parts where the bearings and gears are, you get a chance to get multiple samples that tell that story. One place that's grease lubricated that you don't get that way is going to be this valve stem. So this layer of grease that's on this valve stem, it's really important as well. So let me show you this other tool that we have available. And this is the stem thief. So the stem thief was something that I developed in response to, fortunately, sitting down at a table with some really sharp people from Constellation Nuclear Power, who are responsible for the MOVs in their organization. And, they were asking a question: how are we sure we're getting good relubrication of these valve stems? Particularly when the stem doesn't move much and we don't have a lot of access. So down inside here is where the stem nut sits and engages in the stem. And so when you do get stems that can be stroked up and down, or valves that can be stroked up and down, you could take the portion of the stem that's normally engaged with the stem nut and then run that up until it's physically acceptable. And then we could pack some grease into that and then run it back and forth and kind of hopefully drag some grease down inside. But what if you can't change the valve position? What if this is only a short stroking valve or a butterfly, like a quarter turn valve? Then you don't ever get access to those surfaces. And this was the dilemma that Bob Breithaupt and Elizabeth Hoffman were dealing with at Constellation at the time. And so I said, let me understand the challenge first, but let's see if we can't come up with a tool. And working with Gary Tilton, who has worked here for a number of years and has since retired, we worked together and came up with this design. And so the first piece of the design is an adapter ring. And this adapter ring has the same pipe thread that this section of the actuator has. This is going to be where a pipe protector would be. Let me just show what that looks like. I have it around the corner. This is the pipe protector. Curiously enough, it doesn't work on this one because this one came from Japan, so it's got like some metric threads. But basically, this would be long enough so that this would come down over the top and thread in place. And then during normal operations, there's not debris getting on here, and you're not going to bugger that up or whatever. But once we remove that, the pipe thread here is now in that area, and so we can go over the top with this adapter and thread that down into place. Now, we don't have to go too far with it. We just have to get it started. And once we do, let me put this off to the side, focus on my work at hand here, get this thread started. But once we get that down and threaded in place, Now what we can follow up with is this lubricator. And so the design of what we have here, I'll show you. I'll remove this. This is just a dust cover on the end, this plastic dust cover cap. And then inside you can see that there is an O-ring positioned here, a bore inside, and then back up inside that bore is a passageway that has a Zerk fitting at the end of it. And so as I remove that cap, what I can now do is go down over the top, thread that in place until we go all the way down. And so try not to get things too greasy for my demo, but just be able to show you what we're doing. So you kind of get that threaded on there. That's going down over the top. And then as you keep threading this down, we have a little knurled section up here that makes that easier. As you keep threading that down, eventually you're going to go down into that area. What you're going to be doing is going inside of the lock nut. There's a lock nut that holds the stem nut in place. And when this goes all the way down and mates to that surface, it's held in place by the adapter. And then I just bring the grease gun here, I pump the grease down, and it'll actually go down through those threads and push the grease out. When that is accomplished, that's going to take the old grease and bring it down here at the bottom, down where the yoke is for the valve, and where you get that short section exposed stem as it goes down into the valve where the packing is. But in that space on the bottom end of the stem nut, you're going to be able to take a sample. And for that, we have these kits that we send along with the Stem Thief. A couple components in there. You'll note that it's in a sealed pouch, and so I can tear that top of the pouch away to gain access to the components. And a couple things I'm going to remove from that. One is going to be this spatula. It's kind of specifically chosen for its shape and design. On this end, you've got kind of the spoon section, so you can push the old grease and the old debris out of the way, and then flip it around and grab the grease that is now coming out of that component since you've been pumping the grease in place. And this is the Grease Thief. This is the Type 1 without the stinger probe on there. So what I'm going to do is thread that onto, or just kind of push that on, or just kind of a push fit onto this device that we call the GT filler. And a GT filler takes the place of, say, a syringe or something like that, and it gives you the ability to kind of hold the Grease Thief here, and then as you get the grease, kind of take it off of that surface, come back, and just pack it into this cup. You can see the piston down inside. And you don't quite fill it up to the top, but as you go up to the side here, you'll make kind of a little cone-shaped depression, which is where the plunger goes. And then that plunger goes over the top. That gets pushed down, and as that gets pushed down, that'll push the handle back, push the piston back, and this will be all filled with the grease that you sampled, and that gets a little yellow cap. So now you've got something that can go on to the laboratory, be tested, and tell you exactly what's going on there. Or you can do some testing on site. Now, for this particular cited example, for the NRC letter that was written, there was just some kind of observational type testing done on site where they're just kind of checking it for tackiness and feel and whatnot, and getting a general idea of its condition. The challenge with that is not everybody has the same level of experience of knowing how hard is too hard, how soft is too soft, what does the new grease feel like, how hard can you squeeze, all of these variables. And so but it is important to be able to do some testing on site, kind of turning around right away, right? So we've developed a small portable lab that we call the Pocket Lab. And the Pocket Lab can go on site. It can measure the wear metals that are present from an induction coil that's there using the Poseidon FerroQ solution. It can also has a colorimeter, so our Grease Thief colorimeter is there, and it will measure the color profile, the optical spectrum of the grease relative to the new grease. And it's done by a handle that squeezes the grease down to a precise film, 35 100ths of an inch, 135 1,000ths of an inch. And then at that thickness, the light that passes through is absorbed by the grease. It's compared to the new fresh grease, and we can see how that darkens, ages over time, and so on. And then the final piece that is in this Pocket Lab is the extrusion die. So there's an extrusion die that goes then on the end of this grease thief, and then you squeeze that back out, force it out through that opening, that kind of thin film channel, and it gives resistance to movement. And so that resistance can be compared directly under identical conditions, temperature, the extrusion rate, the force, etc., to the new fresh grease. And so we can actually quantify, what do we really have here? And really that's helpful when you're asking someone, to get involved and make a decision. First off, give them the right tools to get a sample. Why is it so hard to get a grease sample? It's because grease behaves different than oil. If this gearbox was just filled with oil, you could open up a valve and let gravity do its job, and it would, pour out into a bottle, and you can test it and all that stuff. Got to make sure you don't get a dead leg or a little crud trap in there. But you take those efforts and you can do that. But grease stays in place. It's designed to stay in place, and that means it's fighting our efforts to get that sample. So you can't just jam stuff around in there, whether it's a straw, tube, whatever. You need something that precisely positions and then cores the sample that you need to take. And then from that, there's a lot of subjectivity to just handing someone a sample and saying, is this good enough? Well, how does it look? Well, it kind of looks like the grease. It looks darker, but I guess it's supposed to get darker. Well, how dark is too dark? All these questions. We take that guesswork out of the equation, and give you the tools that allow you to quantify things. So I wanted to share with you today. I think it's really timely because plants are now dealing with the kind of fallout of this letter. Like, how do we respond? How do we make sure we don't get into a similar problem where we're making judgments on the condition of equipment without the proper sampling tools, without the proper analysis tools? I wanted to share that with you so that people can formulate a response and know that there is a long history of proven performance with these tools that I've shared with you today. We're also helping out with the restart of a nuclear power plant not far from us here. The former 3 Mile Island nuclear power plant is being restarted as the Crane Clean Energy Center. It's one of these efforts to address the increasing demand for power from these data centers and other demands that are out there. But we're in there, and they have the tools. They have the grease thief. They have the T-handle sampling tools. They're pulling samples from the MOVs that, like these, have been sitting for years unused. And this is that question: what is the condition? Do we need to tear these things completely apart, remove all of the grease, clean them, and then start from scratch? It's a big ask, especially if some of them are in a condition that they can be tested now and operated and checked with the motor current and the other tests that are typically done. So these samples are coming regularly to our lab here, so we can do that testing, and it's something that's available, and a really important thing to do when you're putting your faith in these components. Not just if they've been shut down for a while, but we're extending the life of a lot of plants. The nuclear power plants have these in them. Originally, the licenses were often around 40 years. Now we're into 60. Some are getting extended into 80, perhaps beyond. And now you're into this extended life, and you just want to have the confidence that you've got the data that says we're good to go. We can continue to use these components, keep these plants that are so important running, and have data that backs it up. Not just a guess, not just that's some grease that was drug out of there. No, it is the grease that matters. It's the grease that's coming from those critical surfaces that's going to allow you to assess what its condition is. And when you really need to back up that assessment, you want it to be numerical. You want it to be independent of judgment and vision capabilities and all of these things and experience level of your personnel. Take the measurement, have the measurement come from a good sample that's representative, that complies with the standards that are there for sampling. Not only did I reference the ASTM standard, but you go back about 10 years or so ago, and I worked with Nick Camilli at EPRI to author a report called Effective Grease Practices. And Effective Grease Practices is a kind of a handbook for the power generation industry on how do I grease things, how do I re-grease them, what do I use, how do I know if I've done that correctly, how do I test greases. And so if you're in the power industry, if you fund the EPRI, and even if you don't, it is now in public domain. So if you go to EPRI.com, look up effective grease practices, you'll see that guideline. You can download that today, whether you're an EPRI funder or not. But in that, you'll see we used these very MOVs, which are operable here. I can power them up and cycle them back and forth. And then I even created conditions here of a fault. So this particular motor here, I went in and put some shims in to deliberately misalign the pinion to where the worm gear is, so that we would create an increasing wear condition, a wear rate. And then is the grease thief samples that are taken from this going to show that? And like immediately you could see a change in trend. So it just really validated this idea that you take the right sample from the right location and you do this kind of analysis. You can rely on this data, right? This letter from the NRC should not say, hey, we've got to stop sampling grease. We've got to ignore it because it didn't predict this failure. No, recognize that the problem was in the sampling, that the sampling was not done correctly. It didn't take advantage of the tools that we have here and the methods that are developed and the standards and the research that's been done specifically on MOV limit torque actuator gearboxes, right? So the answers are here. I want to make sure that there's awareness. I wanted to share that with you today. And just know you've got answers, you've got tools. We can do it together, and we can really monitor the condition of these really critical assets going forward. I'm going to ask Sonia to come back and join me. She's been listening in today.
Hi.
Follow this along, Sonia. Good to see you again.
Nice to see you too. And I mean, oh my gosh, so many good, I would say good things happening within the industry, because I did not know that people use tie straps to get that grease. And I think that's not, I'm glad that you're highlighting it and letting them know that they should not be doing that, because that's definitely not what we want to do in the industry. So, like,
Yeah,
this session today was very informative.
yeah, you make a good point, and one of the things that scares me a little bit about that letter is that, like, it says going forward we won't use tie wraps anymore. We'll be using a piece of plastic tubing.
Okay.
It's, it's different. Um, and unfortunately, we've done some testing in the past where we've
Hmm.
shown that is not adequate. And listen, I'm
No.
not knocking anybody because this stuff is not intuitive. It's not
Yeah.
easily understood, right? Like how grease behaves. But this is something I've been studying for
Yes.
30 years. And what we have found is, yes, grease is unique, behaves kind of in a unique manner, but
Hmm.
once you understand that, you understand the particular machines that you're looking at, components that you're looking at, you understand how grease flows and moves.
Yep.
You can design a system that
Yes.
reliably gets that sample, but it's not an easy thing, right? And I
Hmm.
think it's just you put a tie wrap in there, you pull it out, put grease on it. That is a sample. It's true, right? It is a
Hmm.
sample. It's just not the one that's going to tell the right story.
Yeah. And if we are investing so much in our equipment, we should just invest a little bit into the sampling of it, because we want to preserve it. And I love the work that you're doing with the nuclear power plants. And that's very exciting because those things have been around for quite some time.
Oh
I can
yeah,
only imagine what they've seen.
right, right. Yeah, I think in the U.S. anyway, most of the construction happened like in the late '60s, early '70s in the United States, um, leading right up to the accident at 3 Mile Island, and
Right.
there wasn't a lot of building past that. But that's changing. There just
Mm-hmm.
two new units were brought online in Georgia at
Right.
Plant Vogtle. So that's a new plant. There's talk now about small modular reactors, a bit of a nuclear renaissance coming. But between now and then, we're
Mm-hmm.
going to rely on these plants because they are, low carbon output,
Right.
uh, reliable, kind of base loaded capability that we really need for
Yeah.
the coming demand, and doing so without a lot of carbon emissions and so forth. Um, but to do so, obviously, we want to do so safely and
Yep.
reliably. And it comes down to data. Do I have the data that answers that question?
Yeah.
And anything like these critical motor operated valves, or say fan bearings, certain pump
Right.
bearings, anywhere where we're doing that grease, we've got those critical grease components. We need to be thinking about, can I get a sample? How do I get it? What
Mm-hmm.
tools do I use? Today, I just showed a couple of
Yeah.
examples. Um, but this is our kind of
Yes.
kit box, that we use, and you can see on here I've got some QR codes for
Yes.
videos that I've made for using
Very
this.
cool.
But right on there, what have we had since almost day one as a
Yes.
solution for the grief? It's the MOVs. It was
Mm-hmm.
one of my first applications, and so and then to know that the trusted research arm for the whole industry,
Yes.
Power Research Institute, has published on this, has done the research, has said
Mm-hmm.
this works, this is the tool, and it's out there for everybody to see. So it's exciting to see, these changes, these demand, this ongoing effort, but to be here with a solution
Yeah.
right time, and that's why I want to do this today. Knock this out.
Mm-hmm. Yeah.
People, let the folks know who are dealing with this letter that says you got to be careful about this. It's like
Yeah.
you don't have to think it through. You don't have to wonder what we're going to do and whether it's going to work better than what we've been doing. The answer is here. The data is here. Um, it's just a matter of getting it, bring it to your plant, and of course, just like with everything, Sonia, that we want to be a partner in this. We want to answer
Yes.
these questions, not just like ship something out and you
Mm-hmm.
know for the best. It's like, what do you encounter?
Mm-hmm.
You send some samples back to us. We can do the testing. We can, like I say, we're doing testing every week now.
Right.
3 samples right down the road here. We can share that knowledge and expertise, and
Yeah.
hopefully we can get the word out and we can get some more partners
Yes.
going to get good solutions.
Yes, because I think with that letter going out into the industry, some people may be a little bit scared. They may be thinking, "Oh my gosh, what am I going to do now? What am I going to use my tie wraps for?" Um,
Yeah,
yeah,
ponytails,
so
or actually
anything
what they're
good.
designed for, electrical equipment, right? That sort of thing. But no, and I'll tell you, I've done this when I worked in the plant and I was in
Hmm.
maintenance. You would see things from time to time that you had to
Yeah.
come up with a better method. And it's always
Yes.
like, okay, I used to do this, now I'm going to do this alternative method, and you use your knowledge and your
Hmm.
insight, and you hope that it's an improvement. You
Yeah.
hope that you address the things that you're worried about. Just the nice thing here is you don't have to hope. There is data. There's a report. You can reference a report. There's an ASTM standard. You can follow the
Right.
ASTM standard. And you can see me actually using it on MOV.
Yes.
That's what gives you comfort that like I've evaluated it. I've got a good thing
Hmm.
going forward, and I'm confident that we're protecting our plant in the future.
Yeah. And I think that's one of the most important things, Rich, because that's what we're here for in terms of trying to bring the awareness to the industry for those people who may not know yet, those people who are, still maybe want to try that plastic tubing that was recommended. There is a better way. There's a way to actually find out what exactly is in there, and there's a process involved. So get some information, and Rich did a very good demo earlier with this session. So I loved it totally.
Yeah, thank you so much. And I did tie in the stem thief, right?
Yep.
A tool for relubricating the valve, but from the standpoint of trying to put new grease on the
Yeah.
stem, but awareness that it also gives you a sample. It allows you to see that as well. And so the challenge here is that these are generally custom made. So we don't have a
Mm-hmm.
bunch of them sitting on the shelf because we need to know for each person, each
Yeah.
application, what size valves they have, stem heights, all those things. So I just encourage you, if it's something you want to use going forward, get in touch with us early. Give us a
Yeah.
chance to gather the data and the dimensions and start working on those solutions for you so that by the time you come up to your next outage, you're going to have a
Mm-hmm.
much safer operation. You may be able to knock stuff out of your outage. Um,
Yep.
uh, the folks at Palo Verde know this. They've been doing this for, I don't know, 7, 8 years now. And that's why we call our sample kit the Palo Verde sample. Um, and it's just, let's start with what they have and what works for them, and then
Mm-hmm.
take what else you need. But the stem feed is the other part of the solution. All of it available. Reach us through our websites. Some of this going out on LinkedIn, so you can direct message.
Yeah.
And a couple folks have done that already at some of the other plants. I have a New York nuclear power plant, a couple others out there reach out to me already about this, and we're
Nice.
answering their questions. So we're ready to go. We have the
Yeah.
solution, and we just want to get with you, engage, and help you find the answers.
Yeah, don't wait for the plan to go down or to be in or for your tie straps to finish. Let's try and get it done the right way,
Right?
properly sample, and actually trend the data because I know sometimes, especially with grease, it gets that second look and it's like, okay, well that looks pretty okay. But looking pretty okay and actually having data points are two different things.
It is.
And being able to trend it can help you so much in terms of understanding what is happening in your equipment. If you have any wear happening, if it is that you need to change out your grease earlier than you should, and if something is like damaging your equipment, wouldn't you want to know that? Of course, you'd want to know that.
Right. Right. And a lot of times, someone comes along with a new solution, and
Mm-hmm.
they're going to, yeah, it's the best thing ever, and but here we're not standing behind that. We're standing behind EPRI,
Yep.
what they've published. We're standing behind our customers like Palo Verde and
Mm-hmm.
folks at Green Clean Energy that are using these capabilities. And so it's here. Even the Pocket Lab solution is out there
Yes.
for those who want immediate results. Or something a lot of people don't have to deal with, Sonia, is in the nuclear power plant.
Mm-hmm.
These valves sometimes they're
Oh
in
yeah.
radiological areas, so there might be some
Yeah.
contamination and so forth. Then you
Mm-hmm.
can't send that
You
sample.
can't get it out.
So you can bring the Pocket Lab. You just need a flat level surface, about 2 foot by 3 foot, and you're
Nice.
testing greases, and you're
Yeah.
getting, numerical values out that, like you say, you can trend or you can put up
Yep.
for comparison. It's not someone holding it up to the
Yeah.
light, looking at the fingers and hoping they have enough
Hoping for the
experience
best.
to know what bad grease looks like. So thank you for your time. Thanks for joining us.
Yeah, anytime, just let me know. And like, I thank you for informing the industry and keeping them on their toes and helping them to realize that we have things that are available that can be used, and there's a safer and more efficient way to go about these things. So, always thanks to you, Rich. Thank you for sharing.
Thank you, and stay cool.
Yeah, I will.
All right. Take care.
All right, bye.
All right, bye now.